First of all, I would like to thank Jaime Vaz for accepting my application, even though it was after deadline. And I would like to tell you something about some work we did with Dirk Arts from Brussels and some students of mine in Gdańsk, in Poland. Apparently, the idea is new. So we published a few papers. I brought a few reprints if you want. Just feel free to take it. And the idea, the philosophy behind this kind of approach is that we are trying to answer the question if it's possible to implement quantum computation in systems that are not quantum, right? So this is the idea, roughly. And there are reasons to believe that this should be possible because the so-called quantum structures, when people hear of quantum structures, quantum probability, quantum logic, and so on, they often associate this with the micro world, whereas it's known that there are classical systems that from a certain point of view can be regarded as formally quantum, which means that you can have a mechanical system that exhibits quantum probability, quantum logic, and so on. So I insist that we are looking basically for a system that are quantum from a certain point of view, a certain formal point of view, but they are not necessarily described by quantum mechanics. Why? Because there is a problem with quantum computation that quantum computers are, first of all, they don't exist. That's the first problem. Yet, second problem is that even if they will exist one day, for the moment it's basically completely unclear how long will they work, which means that they are extremely sensitive to noise. Yeah? But basically, if you have noise in such a system, then it kills quantum computation almost immediately. So perhaps there are other systems that could perform something which we call quantum algorithms. And I think that the idea behind this talk is that we can formulate quantum algorithms in a formal setting that is completely unrelated to quantum mechanics, which means that I will not use Hilbert spaces, qubits, unitary operations. Instead, I want to use multivectors. Therefore, any system where you have some geometry is a candidate for a system in which you can implement, in principle, a quantum algorithm. And immediate explanation that, as you can see from this place, from this formula, the number of bits is equal to the dimension of the space. I assume this is a Euclidean space, but that's not very important. Later, I will add two dimensions. So I will have A0 and in addition one dimension AN+1 because I need it for certain reasons. A0 will be needed for quantum structure, for complex structure. So this is what I call comps instead of blades. So this is a blade, right? But this instead of speaking blades in a binary parameterization, I prefer to speak about comps, and there is a certain idea, geometric idea behind it. So first of all, a brief digression immediately from the very beginning that comps, of course, can be multiplied because we have geometric algebra. And that's obvious, basically what happens, but from the formal point of view, it's quite interesting that if you have two comps with certain binary indices, then if you multiply them, then you obtain, of course, a new comp up to a sign. Well, okay, sign is uniquely determined, of course, by the binary indices. But here you have n-dimensional addition mod 2. So this is XOR, exclusive alternative. So this will be, in a moment, needed for some relation of this to some works, some ideas that already exist for 20 years, I think, or 10 maybe, in the literature. So, but just to show you why I think comps is a good word for calling these binary parameterized objects. So, and actually, this is one of the implementations. Of course, trivial, mechanical, and very primitive. But I think that if we if our goal, ultimate goal, is to find a working implementation, then it's good to contemplate various possibilities. So this is just really, you take two comps, really such with broken teeth, and multiply them. Each time, you just move them, and you count how many times the teeth met. And each meeting is a change of sign. And finally, when they are brought to the same position, the same teeth annihilate, and this is the result. And this is formally what happens, right? So you can see really a comp with two teeth here, and the sign minus because you had three sign changes. Now, the main idea, basically. So, in quantum mechanics, we are dealing with states of this form, which means that we have a certain number of bits. Such objects are tensor products of the so-called qubits, two-dimensional complex vectors. Now, in binary, I can take a multivector like this in terms of comps, expressed in terms of comps, and of course this is this kind of multivector. So, as you can see, all states of quantum mechanics can be mapped into multivectors. So this is the first idea. First statement is that any quantum state can be written into a multivector, and vice versa. Any multivector can be mapped into a quantum state. Second main statement is that which I will show later, that all elementary quantum gates can be formulated in geometric algebra setting, which means all elementary, which means that any quantum algorithm can be formulated in this language. So we have a complete quantum computation here, without quantum mechanics. So, of course, we need more dimensions than just three. And this is, of course, a problem because we are not accustomed to thinking in more than 3 or 4 dimensions. And I think that one of the most fruitful ideas is to think in terms of configuration spaces from classical mechanics. Because if you want to have 1,000 bits, for example, then, for example, you need a Euclidean space whose dimension is 1,000. So how to do it? The simplest way of thinking of this is, say, to take 500 two-dimensional particles, right? And then you indeed have this. So here we have an example of a 6-dimensional space. You have two particles. They are denoted by different colors, and you have two basis vectors for each of the particles, and then these are oriented surface segments. These are oriented volume elements. I think it's better just to write in terms of just to write edges of these multidimensional objects, because then you have a set of colored oriented polylines, which is very close to graphs actually, but not quite the same as graphs, which was the first day by Stacy. It was discussed. And so I think there is a link. Now, so this will be one of the ways of visualizing our quantum algorithms. So we can play a little bit with this, and of course one can illustrate various all arithmetic operations which we need can be shown in such a graphic way, but it's not very important for us anyway. Now regression, second regression, which is actually it was a starting point for the whole business, because I showed you that if you multiply two comps, then you obtain a new comp whose indices are just sums mod 2, n-dimensional sums of mod 2. And this kind of structure was already used in neural networks, so-called distributed representations, and they were really, this is something like, I'll show you in the next slide how it looks like in geometric algebra. But basically, this is the kind of noisy coding of complicated structures. It's used in coding of sentences, for example. Syntax can be coded in this way. In geometric algebra, you can perform something similar in geometric algebra, of course. And now the situation is slightly simpler in the sense that here you add. So you take long unstructured strings of bits, like 10,000 long, then you add them mod 2, and then finally these things are added by majority voting addition. So this is what they do. And it's really possible to compress a complicated structure into a single binary string and then decode from this string, which you can decode this information in a certain way, and it's used. It's used with ordinary computers. Now, the first observation that led to this framework of quantum-like computation was that when we realized that we have a very similar situation actually because of this adding mod 2. So now we can just take comps, they are multiplied in a geometric algebra way, so this is just a geometric product and this is the ordinary addition, and then you get a very similar structure. This paper is submitted to Journal of Mathematical Psychology, actually, and I think there are reasons to speak to psychologists also about geometric algebra, because in my opinion, geometric algebra is a certain formal algebraic way of representing understanding relations between geometric objects. So you can take two vectors and you take something two-dimensional and you, in a sense, understand that this two-dimensional object is composed by taking one vector and shifting it along another one, for example. So I think geometric algebra for psychologists, especially mathematical psychologists, might be very interesting, in principle at least. Now we are back to our quantum algorithms. So first of all, I need my Clifford algebra is real, but I need complex numbers. But I don't want them. Yes. So I simply do what can be always done with complex numbers. That instead of a single complex numbers, I take two real numbers. So two real numbers means I have to add one bit. This will be. It will be shown sometimes, or sometimes it will not be shown, depends on the problem. But I will not use this bit, the 0th bit, for coding. So coding will be always performed on these bits. But then, because I have this complex structure, I can now map into my real geometric algebra all complex state vectors. So I really have all states from quantum mechanics. Now, this is an example. So we can take the so-called one of the 2-bit entangled states. Entangled, in quantum terminology, means that there's not a product state. You cannot express it just as a tensor product of to 1-bit state. So this is an example of such a state. Well, it has all the peculiarities of quantum mechanics. So it's entangled, and in addition you have a complex phase. Now, so we have 2 bits, therefore we need two-dimensional situation. Now we have a complex number, so we add one more bit to have this doubling into real and imaginary parts. So this is just the bivector in a 3-dimensional space. 0, 1, 2. B0, B1, B2 are the basis vectors, and this real object exactly represents this quantum state. And of course, you can do it with all states. I will not show it. What to do with this, but all apparently counterintuitive objects like the so-called Bell basis, Greenberger, Horn, Zeilinger states, and so on. And in particular, teleportation can be shown in this language in an easy way. Now, in order to have quantum algorithms, I need gates.
As a question for your meaning of teleportation, is this related to the Einstein-Podolsky-Rosen paradox?
Yeah, sure. This is an example of Einstein-Podolsky-Rosen state, right? So this is, yes, I will. This is quantum teleportation in this sense, which became famous in recent years. I will show at the very end. I will show you the teleportation. By the way, this famous teleportation, which resulted in this result of a group, Anton Zeilinger from Vienna, ended in the Guinness Book of Records. Yes? And actually, it was a 3-bit problem, so it can be visualized in 3 dimensions. So it's simple, without complex numbers. So we have now. I will show 3 slides, just mentioning what we should have in such a framework. So first of all, we need the so-called Pauli gates, X, Y, Z. They act like Pauli matrices. So here, for example, this is X, which is not, basically. right? It takes 0 into 1 and 1 into 0. This one is not very important because it can be combined from these two. Z gate is important. It's a sigma z basically. It does not change the sign if you have 0 and changes sign if you have 1. So it is -1 to AK. So this is one set of single bit gates. Now we have 3 more gates which are important. We will not use them, but just I show them that they are constructed in these papers, of course. In order to have really any quantum algorithm in this language, you need these gates. So this is the so-called Hadamard Gate, which is just a sum of x and z. This is phase gate, and this is pi 8. That's how they call it in quantum computation books. So this multiplies by I, and this multiplies by e to I pi divided by 4. This is what we have to have. We have to implement it in geometric algebra. I'll show you how to do it, but just... And then, important class of gates. These are 2-bit and 3-bit quantum gates. So we have controlled NOT. This is an example of controlled NOT. So this is performing NOT operation on the second bit if the second... It's performing the NOT operation on the first bit if the second bit is 1. If the second bit is 0, it's switched off. Right? So the second bit is switching on and off the NOT operation. So it's controlling the NOT operation. So here, I did not explain. This is negation, right? So this is, it should be explained on the slide, but I put it in a different place. So 0 prime is 1 and 1 prime is 0. 3-bit control not. So it's twice controlled. It's the so-called Toffoli gate. And if you have all of these gates, you have everything in quantum computation. Now, I would like to show you something which already shows that this 3-bit gate is interesting from the geometric point of view. Because if you think of these, so we have a comp with 3 teeth, which means B1, 2, 3. So this is the volume element. Now, if you act with the Toffoli gate on this, you get B2, 3, which is one of the sides, right? So you squash this cube. And the inverse operation just reconstructs, not from this, well, okay, I didn't show it, probably. It's not show, anyway. So this is an example of inverse operation. You have wall B1, 2, and then by acting with the Toffoli gate, you just reconstruct the cube. So it has clearly a geometric operation. In geometric interpretation. So now we know what we should have. So we should have x, y, z. Y is equals to x times z times I, up to some sign perhaps. And we want these things, and we want to implement this in geometric algebra. How do we do it? So it turns out that we have to add one more dimension to our to our Euclidean space. We will not use this dimension for coding. So it will never occur here in such a state. It could be called, sometimes Z, sometimes C, because I was pasting these formulas from different papers. So there's a slight conflict of notation, but not very important. So Z could be treated as C. There are certain reasons for calling it Z, but because it's a general combination of imaginary and real comps. But anyway, so we add one more dimension. Then we have these objects. And then, as you can see, negation of a performing NOT operation on the bit number k is just a geometric algebra operation. So that's really what happens. This is important because otherwise we would have certain changes of sign. Right? When we move elements from geometric algebra, it depends how many times it hits a basis vector, it would change sign or not. I want to get rid of the sign change. So I had to introduce one more dimension to make sure that I don't have the problem. So here it's explained as prime. Now this is essentially the X operation, right? Because it exchanges 0 and 1. This is essentially the Z. No, not essentially. This is Z operation because it multiplies. If this bit is 0, it multiplies by 1. If this bit is 1, it multiplies by -1. And then this is a useful object. It's a kind of projector, which just multiplies by the value of the bit. You can construct it as a sum of two comps in this language. Now, the main result is that all 1-bit, 2-bit, 3-bit gates can be constructed by means of this projector, which multiplies by the value of the bit. This is gate Z and I, of course. For example, this is an example of how to produce a controlled gate. So you take any gate. It's not necessarily the Pauli gate, just any gate, and then not necessarily even 1-bit gate. And then this is a gate which is controlled by bit number k, right? So this is in terms of this operation here, right? So this is how it works. So since we have all elementary gates, we can perform all quantum algorithms here, right? So all quantum states can be made into multivectors, and all quantum algorithms can be performed. So now, first example of something which is very similar to what happens in quantum mechanics. This is a typical starting point of many quantum algorithms, and the idea, how it works. This is the n-fold Hadamard gate. You take n zeros, which means, say, for example, n spins in pointing down, or n systems in their ground states, for example, and then by n operations, essentially, performed on each of these objects, you produce a superposition of all binary numbers of n bits. So this is an example of this acceleration, which you can find in quantum computation. Now, what happens if we do it in the geometric algebra way? We have the same, right? So the same acceleration, exactly. And the trick is that the superposition of all the possible comps is just a simple geometric product of such superposition. So really you have n multiplications, n minus 1 multiplications, or n, because we have this, which is not very important, and a certain amount of additions. That's it. So clearly you have an exponential acceleration here. So it shows that there are hopes, at least, that such computers could work really as fast as quantum computers. Now, of course, there's a problem how to do it in practice. Yes, because if you want to perform one Hadamard gate on say the last bit, then it's a sum of two terms. Now, so you do it. So we have two operations for this. Now, you want to perform another Hadamard gate, which is, again, two operations, right? But now you have 2 times 2, and it depends how you treat it. If you really treat it as a single multivector or as a sum of two different multivectors. So if you have to process each of these multivectors, or blades, if you have to process each of the blades separately, then you will have exponential complexity of the problem. But if you treat each of the multivectors as a single object, which I think is the correct way of thinking in terms of geometry here, then you will have this speed up, typical of quantum computation. So the moral. So we have to make sure that all these quantum gates really act on geometric objects. No? So it's not like splitting a multivector into 2 to nth component and then manipulating with each of the components separately, because then it's slow, obviously, right? But if you treat it as a single geometric object and you can just make a single operation, then it will be quick. So it depends on how we implement the geometric algebra. Now, another example of parallel computing, because it's parallel, right? You take a superposition of 2 to n binary numbers of length n, and then you just, this is a single multivector, you act from left and from right, then you, on the whole superposition of all these numbers, you change sign only on those numbers that have 1 in this place, right? But simultaneously, you can now manipulate a little bit with this, and this is the result. So again, how many operations do we need? Well, I would say that we need probably 3 operations, because we have or two even operations, because we have a multivector and one multiplication, another multiplication. That's it, probably, right? But on the other hand, you can express it in this way, and still you have an exponential speedup, right? Now, the famous Shor algorithm. Famous because it was formulated in 1994, and actually it was the paper by Shor triggered basically the whole domain, because Shor algorithm is an algorithm for factorization numbers into primes, and it's quick, right? And we know that this this factorization algorithm is an essential part of how it's called, of public key cryptography. What's the name of the algorithm of this system? RSA, yes. So, since Shor showed that if we have a quantum computer and we can do it quickly, it means in polynomial time, then, we could break RSA. Of course, then armies got interested in this, and suddenly it became an interesting field of research, and it was 1994. Now, how it works, roughly, there's the algorithm set only at one place, basically, or two places, perhaps, uses quantum mechanics. It's a mixed classical quantum algorithm, and the idea is simply to find the period of such a function. Unfortunately, I took 2. It could be any number which is coprime, and I think is any coprime number with 15. 2 is misleading because we have too many 2's here, right? In this example, because here is 2 to 4 minus 1, because these are all it's sum over all the 4-bit numbers. So this 15 is not related to this 15 because it's just how many bits you need to encode 15 simply. Right? So that's not slightly misleading perhaps. But how a quantum processor is working. So we have a hypothetical quantum processor which performs all these. It can be formulated, this algorithm, in terms of elementary gates. So this is really an algorithm. And in the case of 15, it looks like this. So we have a certain system on which we put into which we process by our quantum processor, and it produces such a superposition. And then we make measurements of numbers. And the problem, and we want to find the period of this function. So the period of this function is seen already. You can see what was the period. It's 4, right? All these numbers are shifted by 4. But if this is a quantum state, you don't see it, right? It's just a system in superposition of different results, and you just make measurements, and measurements just produce numbers. Which numbers will be produced here on the left-hand side? All numbers will be produced. So you cannot directly read this state. You have to do something first, and you have to remove this shift. That's the idea of Shor, that we remove this shift by quantum Fourier transform, which is basically the fast Fourier transform, but implemented in this qubit form. And then, we extract finally the period of the function. The period is 4. The result, factorization, is given by 2 to x divided by 2 plus minus 1. So indeed, if you have x equals 4, so it's 4 plus minus 2, and it gives you 3 and 5 exactly already. So this shows roughly how it works. Now, we have a GA way, geometric algebra way. So we have to have a machine, a geometric processor, which does the same thing as here our hypothetical quantum processor. So in terms of multivectors, the result is this. Now we can try to show it because it's not very readable. So I have now 8 bits. This is one register which needs 4 bits, and another register which needs 4 bits also. So we have 8 bits, so we have an 8-dimensional configuration space. Now, in terms of when our geometric processor produces such a multivector. This is bag of shapes, or bag of polylines. And so this is the state. This state, which is analogous to what was produced by our quantum processor. Now, I told you that in quantum processing they need to perform Fourier transform to get rid of some shit. We don't need Fourier transform here anymore because we can perform measurements on the system in a different way. First of all, it's a multivector, so it does not collapse after a single measurement. Right? It's a geometric object. We can do different things than in quantum computation. So what we do, we first select all those blades which contain this. It was basis vector number 8. So this is this vector, right? The multiplication. So we have zeros and here 1. So this is the vector in this notation. This is B8. So we say. No, it's just I had to write in 2D something which is higher.
Just to make them different?
Just to make them different to see what happens, yes? I could, angle is not important if I have colors. But when you try to publish a paper, then you have to pay for colors, right? So that's a very, impractical. But anyway, in physical review, you can select an option color online, so you can have both. But this you can see anyway. So we select this part. Now we have to. So selecting this part means, coming back to this, we select this fragment. And to get our number, which we are looking for, we have to first find the smallest non-zero number in this collection. So this will be our 4, which we would like to find. So here. So we have all these numbers. This is 0 number in the sense that on the first 4 bits from left you have zeros. So the number we are looking for is this. So our algorithm just produces, so our quantum processor produces such a multivector, then we select this by certain projection, then take the first non-trivial element here and see what was the result. So we selected this, and this is, if you look at this basis, it's B2 times B8. So it means that you have 0 at the second position and the 8th position. Now, the first half of bits are those bits devoted to this left register. So we just look what we have here, and this is just 0, 1, 0, 0, which is 4, and this is our answer. Right? So this is a completely different way of quantum computing, but still it works, provided we have a machine which does it. Now I my talk will be shorter than 1 hour. So this is now related to the title of my talk, because I said about quantum teleportation. Quantum teleportation, I will explain in detail in a minute, is simply one of the possible quantum algorithms. So since this is a quantum algorithm, I can just do it in a geometric algebra way. So this is a famous experiment which resulted in this Guinness World Record book. By the way, I tried to find yesterday on the internet a link to this Guinness book, and they were very proud initially that they landed in this Guinness book, but now I couldn't find any reference, so they are somehow they are not proud anymore of being selected for this record. I don't know. Anyway, I couldn't find a reference to this Guinness record. But it really became famous because of a very good name they chose for the procedure. Now, how it looks like. So, in this concrete case, actually this is the case which they were investigating in the experiment. So it's a 3-bit problem. So it can be shown in 3D even, right? So this is easy to show. It's so easy that I will not show it. Yeah? But I will just show you how it looks like in geometric algebra. So what's the problem? The problem is that we have a 3-bit system, which means that we have Alice and Bob. Maybe I'll make a drawing. So the situation is roughly like this. So we have Alice, who has her state, 1-bit state, say linear polarization. And then we have Bob, who is somewhere else. And what we want to do, we want to map this state here but not just taking the particle from the lab. More? You don't see. Okay. No. Anyway, we could take the particle of Alice and just bring it to the lab of Bob, right? But this is not what we want to do. We want to do something like teleportation. So we want to kill this particle here and make sure, by sending classical information to Bob, send a set of instructions that he will create in his lab from his particles something which has the same state. So we kill one guy here, send information, classical information, that's important, just a set of instructions, and then this guy is reconstructed in the lab of Bob. So that's why they call it. So let's say this is bit number 1 in the lab of Alice, and then we want to produce the same state, the same in the sense that it will have the same wave function. Unknown wave function, that's important. So the procedure should work in such a way that Alice doesn't know, in principle, which state she wants to produce. Because if she knows, perhaps, she wants to have it automatic in some sense. And there is a resource, a common resource, which is, there is a two-particle entangled state, which has indices 2 and 3. So roughly. No. Okay, so how it works? So we have this initial state. So this is a common resource, just entangled state like this. Then this is a state unknown to both Alice and Bob, somehow created in her lab. And I will show you the few steps of the algorithm because it's easy. So we perform controlled NOT operation. This means that bit number 2 is, we perform NOT on bit number 2 controlled by bit number 1. And then we perform the Hadamard state, Hadamard transformation of the first bit. So we get something like this. And we would like to have in the lab of Bob such a state with 3s instead of 1s here. So we can see the state here already. But we have 3 other parts which are similar but not exactly the same as this. They're different in certain places. For example, here we have 1 instead of 0, and here we have 0 instead of 1. Here we have minus instead of plus, but the bits are correct. Here we have both sign wrong and bits are wrong. So we have to do something with this. And we do it in 3 steps, 2 steps basically. So first of all, we apply a control NOT operation which performs a NOT on the 3rd bit controlled by the 2nd bit. So we almost have the state which we want. Here already we have the state twice, but here we have wrong signs. But we know what to do with the wrong signs. We have to change them by Z operation, Z. Right? And then so we perform, this Z must be performed only on this part and not on this part. Therefore, it should be controlled by the 1st bit. If this is 0, it should not work. It should be identity. If it's 1, it should do it. And what we have, finally, is a state which still looks apparently complicated, but is very simple, in fact. But what's important is that we have the same state always here. This is the state in the lab of Bob. Now we should make some order in it. And then the simplest way of making order is just apply Hadamard Gate to the left, to bits. And when you do it, you obtain something very simple. So you have, in the lab of Bob, we have exactly the state which was in the lab of Alice, but the difference is that it is simply expressed in a different basis. And Alice and Bob don't know.
Yes, the exact question you raised. I have a question here. So these groups, in my view, can be expressed also with verses.
Yes.
So multiplying verses, you should be able to do these quantum transformations.
Yes.
Okay, but this will be a talk in the afternoon about this.
It's exactly the question which Margaret is asking.
So,
so the state 03 is represented by the same thing in the GA version as the state 01, is it?
Well, in a sense, practically yes, because there's a certain ambiguity in number of zeros. practically. Yes.
That sounds a bit surprising that you can't distinguish whether it's the third or the first.
You can, because Z1 is a... Yeah, okay, you can't do it. Yes, that's true. That's one of the differences perhaps with just... Because... Okay, just... Yeah.
Okay, just some programmatic issues. I mean, it sounds like you are in the process of doing this conversion, but there is a lot to do yet, because ideally, I mean, it seems that your interest is getting a full model of quantum computation via Clifford, geometric algebra. However, when you mention those quantum gates as not being simulatable in the proper number of steps, and rather, instead of using polylocality and getting each of the, I forgot the name you use, for each of the factors, and rather making full products, that's already kills the idea of scalability. So you really want to go to, in a way, finding the analog of the swaps to localize the processing, so you have a scalable model. But even more, you want to address issues of complexity of these simulations, because you can simulate, of course, quantum in classical as long as you use exponentially many steps. So the point is, what is the actual complexity of making these individual computations and trying to get the universal gates properly addressed? Because if you indeed can do this, then it's first you have one direction of a mode of computation equivalent to the other, just like people having quantum field theory or diabatic, etc. But if you do the converse, then you have an equivalent model, and actually perhaps the converse is also important to have, since you have this whole machinery of problems of different areas modeled in geometric algebra. You want to have a explicit way of addressing quantum algorithms for this. What is a whole world of opportunities there, right? So you really want to have both directions and their complexity addressed, so you can really say, oh, these are equivalent models, and you can reason directly here. Because when I saw these diagrams drawn, I was concerned precisely with what is the complexity of doing those.
Yeah, sure. So first of all, I think that all quantum computation has been already transformed into this language, because I have all quantum states, pure states, yes, and all elementary gates.
So which complexity?
Well, okay, that's not yes, sure, and this is a crucial, of course, question, yes, and it's as usual. This is the implementation problem. Yeah? So the complexity will depend on implementation. If we can really implement, if we really can have a system that processes the entire multivector, not just blades, one by one, then I think it will be efficient. Right? You probably would agree. That's a similar situation on these graphs.
Actually, it's independent of implementation. It's a theoretical thing, because if you implement the model, it may be a delay from different machinery, but the model itself is independent of implementation, on hardware.
Well, so I have the same in this sense. I just operate with my gate. If gate just operates once, if this is a single step, then I have the same complexity as in quantum computation. But in practice, if I want to take a pencil and just do my quantum computation on a piece of paper, it will not be very efficient. Of course, if I want to do it in Mathematica or on an ordinary computer, it will not be efficient either, because I have to somehow do these geometric algebra operations. So maybe I should take matrices and multiply them, and of course it will be slow, right?
No, of course. You're using a classical computer, so of course
but quantum computation is based on a different idea, that we have a physical system that is doing something for us.
Exactly. So the point is whether the model itself admits this equivalency and efficiency, so you would then think about what hardware will be convenient.
Yeah, sure. So this is
an excellent project. It's just that I think these issues are crucial to be thought. I mean,
I agree that this is an excellent project. Well, there is a subtlety related to excellent projects.
It's a crucial thing.
Can I make a remark about the hardware? who makes digital circuits in hardware, they're developing geometric algebra processors, which on the most fundamental level.
Yeah, that's the direction in my opinion.
The parallel geometric algebra product. So if you combine this with your formulas for the implementation,
Yeah, that's very interesting actually.
then I think you get the speed which is superior to anything else.
Yeah, so if really we have geometric processors, then that's what we need basically, right?
Well, a comment to the question. I mean, on that, you're just basically doing parallel computing. I don't see any reason why that should give you sort of speed up that we're expecting from quantum computers, precisely because of this point. From quantum computing, we're trying to use a different physical principle behind the computation. What you're talking about is just parallel computation, which may be very useful, but it's not exploiting.
But it's an elementary implementation of the geometric product in hardware.
Yes, I understand, but it's just parallelizing it, that's it.
Yeah.
Instead of doing superposition and
Yes.
all the advantages of superposition.
So that's one point. Can I just ask a question about your sort of notation and setup? I wonder if you've looked at the multi-particle space-time algebra way of doing all this. In that, we know that we're able to do some quite interesting factorizations, where you're able to sort of separate off the entanglement part, at least in the two particles. It's work in progress to do it for three particles. I mean, are you able to do that same sort of analysis and things like the Schmidt decomposition and so on in terms of factorization of your states?
You know, I think that in this type of approach, you are treating qubits roughly as spinors are treated in geometric algebra, right? Two spinors. So, right, that's the idea essentially. That in geometric algebra, a spinor is not just a column vector, but something which is a column, which is a 2 by 2 matrix with empty second column. That's roughly how I imagine a spinor in geometric algebra. And my feeling is that this approach is using the same philosophy, that spinor is a qubit, roughly. Yes, and then you map these entangled states of quantum computation just by tensor. You, in a sense, mimicking standard quantum computation in a slightly different language. It was my impression. But here, so therefore, you need all the machinery of quantum computation, like Schmidt decomposition, you said. I don't think that we will not. Maybe we should think of something like Schmidt decomposition, but I'm not sure. Simply, it's a slightly. Up to a certain point, it looks like quantum computation, but then you have basically you have different structures. For example, I don't need to have cosine universality. I don't need to have unitary gates in geometric algebra. I need geometric gates, not quantum gates. So I have this also related to your comment. So I simply at certain moment, up to a certain moment, I can show that I can map any quantum algorithm into this framework, but then I'm no longer obliged to follow quantum rules. I probably might have different rules. And I think that what you were doing with Chris Doran, yes, this work, was more in the spirit of kind of following the logic of quantum computation, but formulated in the language of geometric algebra, kind of a map.
Yeah, but it did give us extra power, and we could do things like factorizing of something which represents a rotor, which represented the degree of entanglement of the two particles.
Yeah, okay, this I should study. Yes, I'm not sure. I'm not sure. Mm-hmm.
Yeah, but the problem is, the quantum algorithms, they are for data that has sizes unbounded. So when you're addressing that and you say, okay, for n, I have here something that multiplies something of size n. But you're not going to implement one for each size. You have to have, for universality, those minimum pieces and how to combine them. That's exactly the question of Hitzer, is because you have one gate, some one gates, and one two gates, with which you generate a lattice that approximates efficiently every quantum gate of any size. That's Solovay-Kitaev theorem.
No, but in practice, quantum computers, 15 was already factorized into 3 times 5 by a quantum computer. Yes, they were able to create a computer with 4 bits.
Yeah, but
so always you will have a finite number of bits in a computer.
Yeah, but if you have an arbitrary number, you want to have the flexibility of with a few generators of gates produce any size as your computer can. So that's what I'm saying. You have a wonderful project. I think this is a crucial issue for scalability to complete a project. You know what I mean?
Yeah, it's a very big beginning of the
Complexity and
project. Yes, so the first paper was published last year, so it's very fresh in a sense. Yes, there are many questions. But I think that to convince people that it may make sense would be to really think of some implementation of yes, so this parallelism, as you stress, is very important to really have something that operates on entire multivectors and not just on a single place, one by one, because then it would be slow. But we are not really accustomed, I think, to thinking in terms of multivectors, even if we have four-dimensional space-time. It's already difficult it's a mental block to say, okay, now I have my Clifford algebra, which is 16-dimensional, and then this is my, like in 1 year unification, for example, right? So we are not used to thinking in terms of multivectors. Somehow we are trained in thinking in terms of blades. Or in your terminology, we are not used to thinking in terms of polyvectors, but in terms of multivectors. Yeah? That's what we do. But this is the difficulty conceptually if you look at it.
We can start have a coffee break. Let's
Okay.
speaker again.
Thank you. This is my fourth